Okay, so I think we'll get started because you have a busy afternoon ahead of you. I'm Wylie from Jülich Supercomputing Center, and I'm going to introduce you to the Performance Optimization and Productivity Center of Excellence, which, has anyone heard of this POP Center of Excellence before? Roughly half, so at least some of you will learn something. Okay, so POP is one of the 14 current centers of excellence. Most of them are focused in particular application areas such as materials science or climate and weather simulation, space for cosmology and astrophysics. You'll hear tomorrow about the multi-scale CoE. It's a little bit like us being transversal, working across and supporting the other CoEs. And the goal of the centers of excellence is to get applications running and capable of using the EuroHPC system, so the Jupyter system, which is being installed outside our window, and the other systems which are already up and running for the last year or so. So POP is a center of excellence focused on, as its name says, performance optimization and productivity, promoting best practices in parallel programming. We're providing free services to people to help them understand the execution of their parallel applications and how they are using the systems that they're running on. And we give you feedback, support as to how to refactor your code, rework your code to optimize and use those resources in a more productive way. The services are free across the community, primarily for EuroHPC users, but also for the wider community. The Center of Excellence has been running now in 3 phases. Started at the beginning of last year in the 3rd phase. It's coordinated as before from Barcelona Supercomputing Center, and then there are partners, as you see from the logos here, from Germany, from Portugal, from Czech Republic, from France. So a wide set of expertise available from a range of performance tools, a range of parallel programming models, and able to work with a range of applications, as we've done in the past, from academic and industrial users. I'm sure I don't need to tell you this, that parallel programming is challenging. The codes are increasingly complex, the systems are complex to use, and there's a need for a good understanding of how applications execute and quantified information as to where the main issues are and what's the most productive direction to refactor code and improve performance. So that's where the POP Center of Excellence comes in, helping to identify performance inefficiencies. And in our latest incarnation, we also have started to look at energy usage, but that's still very early work. Most of the codes we work with are MPI combined with some sort of threading, and increasingly using some form of offloading to GPU devices. As I said, the current phase of the Center of Excellence started at the beginning of last year, will continue to the end of next year, which is all when the other CoEs finish their work as well. To use our services, there's a website you can go to, popcoe.eu, and there's a service request form. There's a picture of it on the upper right here, where you just put in some basic information about how we should contact you, and some information about the application that you'd like us to work with. And then we'll get back to you and work through the process together, which involves an interaction with you to figure out what is the test case and the system that you're interested in the analysis being done on. Either the applicant does some performance measurements and then we analyze those, or we're told how to build and run the application and then we do the analysis as well. At the end of that process, you get an analysis report, which is then discussed with you, and there's a follow-up process after that to determine whether there should be a continuation to do some additional investigation, some additional analysis, or whether the initial analysis served your purposes. There's all sorts of other work packages involved here to distill the insight from assessments into co-design repository, publish the results if you agree, and make sure that the whole process is working so that it's beneficial to the community. The primary service offered is the performance in us, the parallel application performance assessment. That gives us a basic overview of the application and how it executes on the system. It's looking initially at a set of high-level performance metrics that are looking at various inefficiencies, and If necessary, we'll go beyond that and dive into more of the details as to what are the causes of those various inefficiencies and quantify how significant they are. I think I just continue. Yeah, screen has come back. From that high-level assessment and that first level, it may be that you've already got the information that tells you what you need to do to improve the performance, improve the efficiency, or it may be that there's a need for or interest in a second-level service. So there's correctness checks, which we can do with some of the tools for MPI and OpenMP to verify that you're using those parallelizations appropriately. As I said, there's a new energy efficiency study that we're just bringing up and starting to familiarize with. In red at the bottom, it says this is a shared effort, so it's very collaborative. We need to work with you to understand that we are running the right test case and analyzing the correct part of the execution for inefficiencies and making sure that we deliver the information that's most beneficial to the customer. I mentioned that we have a number of different tools that are developed in the Center of Excellence that go into a lot of detail when required and are able to scale to the larger scales when necessary. These are open source toolkits, the BSC tools, X-Ray Paraver, the ScoreP Scholastica tools, which you'll hear about in the following presentation, as well as additional tools from some of the other partners, such as the Cash-Aware Roofline model from Portugal, Macau, for node level performance analysis, and then there's the Archer and Must tool set for looking at correctness. Those aren't the only tools that we use. Those are the ones that we develop within the Center of Excellence and customize as necessary, but we also work with and take measurements with vendor and ISC tools when those are available on the different sites. To go into the analysis process, the assessment process in a little bit more detail, an assessment is a combination of a code, a version of the code that's provided, running on a particular hardware resource and compilers and environment. So that is discussed and considered with the customer. And then there's a data set. So in this example, it's we're running a heart simulation, heart flow simulation on Mare Nostrum, but that's just one example here. So once we have a test case that is agreed for analysis, we'll do some measurements of it, either with whatever tools are most appropriate. The initial information we get is a high-level assessment, so looking at various efficiencies to characterize the efficiency, look at its scalability, and then going down based on that direction into details of looking at precisely what's going on in the different processes, on the different GPUs, in the different phases of execution. And so that can go into a lot of great detail, but it's directed by the high-level assessment that started the process. So a brief example of the sort of assessment that you would get. This is a code that was running on the SuperMOOC system, scaling from 24 nodes, 1,000 processes at the smallest scale, up to 300,000 processes on more or less the full SuperMOOC system at the time. And we look at the scalability, look at the performance efficiencies within a node, using the smallest configuration as a reference configuration here. So just looking at the runtime shows us that this application scales very well for the majority of its scaling, and it's only scaling, tailing off at the very largest scale, which is to be expected. When we look at the efficiency of the smallest configuration here, we see that the basic execution efficiency is good, although there's a load balance aspect here. 0.8, 0.79 shows there's potentially 20% that could be gained by resolving perfectly, optimizing the load balance. And since this was a brain simulation, studying the flow within the brain, it was a very challenging data set. It was difficult to partition it and balance it across the nodes. So the fact that the load balance is not perfect over 1,000 processes is kind of par for the course to be expected here. What's interesting is if we look at how that changes as it increases with scale, it doesn't really change very much. Sometimes it's a little bit worse, but actually over the whole it stays pretty good all the way up to the very largest scale. So load balance efficiency is something that's inherent in the partitioning, the distribution of the problem here, and it doesn't really change with scale here. When we look at the computation efficiency, with communication efficiency, is using a lot of non-blocking communication here. That starts off being very well overlapped with the computation, so there it's more or less perfect, and it stays very good all the way up to the very largest scales. So that's, again, not a big issue here, not a big problem. What's the other aspect is how the computation is scaling, how the work that's being done changes as you increase in scale. What's here referred to as instruction scaling is the additional instructions that are being executed for processing boundaries and additional things that are necessary when you partition to smaller and smaller chunks of work. And that becomes the biggest inefficiency that we see at the very largest scale. So by that point, we have decomposed the problems to such a scale that the amount of computation within a node is so small that the boundaries are dominating. We also see that this is partially compensated by IPC, so the effectiveness of the computation itself. The data set fits into cache better, so it executes more efficiently there. And so those two efficiencies are trading off one against the other. So that was just a broad example. Once you have identified the overall efficiency, we can then go into further detail, identifying what are the phases of execution, what are the parts of the code, what are the operations that are expensive, whether they're MPI or OpenMP, or in this other case here on the right-hand side, when it's looking at GPU kernels and the time that those take. In this example, we see that the kernels which are in the corners and in the edges take longer than the ones in the interior, so there's a bit of imbalance there. But overall, that's not a big issue here because that's a very small part of the computation, very quick part compared with the overall kernel execution here. In the interest of time, I'm going to skip over going into further detail here and just sort of move on to summarizing what we get. We have primarily focused on MPI, internode performance, but we also look at what's happening on the CPU as well, whether it's vectorization and how the caches are used. We're increasingly seeing more cases where we need to look at how GPUs are used, and we're starting to get more experience with that. Most of the cases we're working with are strong scaling cases where that's the most interesting. Weak scaling is much easier, and some applications are more interested in that aspect. In the last round, and since last year, the cases we've been analyzing have been relatively modest scale, so up to about 10,000 CPU cores and 500 or so GPUs so far. But we know that the tools are capable of going to well beyond that. I wanted to mention that one of the aspects, the aspect that I'm most involved with the POP Center of Excellence is the training task. Most of our training is done through an organization called the Virtual Institute for High Productivity Supercomputing. We've done workshops all over Europe and in other places as well. These are multi-day workshops which are hackathon form. People bring their code, we analyze the performance of their code with a variety of tools, and coach the application developers as to what's the most effective use of the tools, as well as what they can do to improve the performance of their applications. So those are the information from those is workshops in the past is on our website. Just to summarize, we did 4 workshops last year using a variety of different systems. A couple of workshops were in Germany, one in France. The last one was in the Czech Republic using the Carolina system. And that was part of a collaboration with a number of national competence centers in Central Europe, and we're working towards doing another collaborative training event sometime in the course of this year. For that workshop, we used Carolina, both the CPU and GPU partitions, and for the 12 applicants who had codes running on the system, we worked with them to analyze the performance of their codes. Finally, just to mention that we have a tutorial accepted for ISC this year. We had it last year, but we're doing it again this year, a half-day tutorial giving some hands-on experience using our analysis tools. In the scope of that tutorial, where you can only work with pre-recorded measurements, but that's a starting point to understanding what you can get out of our tools and how to use the methodology and tools that are developed in the POP Center of Excellence. So I think that brings me to the end of my time, and so if there's a question or so, I can answer that before we switch over.
Any? Yeah. Thank you. Any questions for Brian? If not, I have one. How difficult is it becoming in the future, you think, due to the growing diversity in hardware? So Jupyter is coming here, is going to be NVIDIA Grace based, which is different enough from what was there before. Not only in terms of instruction set, but also the CPU itself and memory bandwidth, all that stuff. Will probably alleviate some of the bottlenecks you've seen in some codes and maybe bring up others. How do you see that progressing in the future?
Every system is unique with compilers and hardware, and so the bottlenecks change depending on which system you're looking at, and also the test case you're running. All of those are variables that make it challenging to say that this is your particular problem. So we analyze the test case that is provided by the customer, and if there's other test cases, then we'll analyze and look at those separately.
And so based on your experience that you've built up over all the years, you know where to start, you have a certain process. And I think it's not enough to just get your hands on the tools and do things yourself. You really need some experience into where to look first, or what kind of steps you have to take to get to a meaningful result in the end.
It's a complicated process doing the measurements. It's complicated understanding the measurements. We understand that. But the advantage of our open source portable tools is that the same tools can be used across platforms, whether it's the JEDI system or Jupyter system here, Lumi, or the other EuroHPC systems. They all have their own great tool sets, which are specific for those individual systems, but our tools allow easier understanding and a comparison across systems, because our efficiency metrics are platform independent.
A quick comment, because I'm also involved in POP. We did over 350 performance assessments over the past 7-8 years or something. And when you look on a high level, 30% have a load balance problem, 30% have messaging, and 30% is like memory computing. And I don't think this, again, it's all kind of architectures, and I think this will be the same for Jupyter in future. So it's, people are still struggling with the basic stuff, yeah? How to get the load balance right, how to use the network efficiently, how to use the memory.
Yep. Okay, great, thanks a lot, Brian. Switch over to Marcus to zoom in on one of these tools.